Hi everyone, my name is Fabrizio Dell'Acqua and I'm presenting joint work with Cowgill, who's here to answer some of your questions, and Samuel Deng, Daniel Shu, Nakul Verma, and Augustin Chaintreau. The title of our paper is Biased Programmers or Biased Data, a field experiment in operationalizing AI ethics. So the topic of AI bias has been very central in a lot of discussions recently. You might have seen this article by ProPublica claiming that a software to predict future criminals was discriminating against Black Americans. And this, of course, has been the subject of a lot of research. The success of conferences such as FedStar or the New Fork is indicative of that. But a lot of this research has been mostly theoretical. So what we think is missing are empirical papers about the AI development process and their links to biased outcomes. Specifically, we're thinking of clean random variation in programming practices and clear outcome metrics of success and failure, so that we can then causally link these programming practices to the presence or absence of bias. And then we will be able to link these results back to theory and have the results informing theory as well. So, and then zooming out, the broader questions that we would be able to address with this are, why does algorithmic bias arise in the first place? And also, what in practice works to reduce algorithmic bias? So what we're doing in this paper is a field experiment in AI development. We work with about 400 programmers and we assign them exactly the same task, that is to predict performance on a standardized math test for about 20,000 randomly selected people and using 5,000 covariates per person. And the subjects were all placed under 4 different randomized experimental conditions. So this would allow us to attribute the creation of bias code to specific programming practices and also to specific programmers' characteristics. In fact, we have a rich data set of programmer covariates. We know their education, their demographics, their attitudes. All programmers also answered a 53-question survey at the end after completing their machine learning task. So to give you a brief preview of the results, we compare our interventions to 2 benchmarks. The first benchmark is the best one, and it's a benchmark with completely unbiased training data. The second benchmark is a benchmark with data coming from sample selection bias and no technical advice or no additional intervention on the subjects. So first, we observe a positive result in our non-technical reminders. I will go through this in detail, but these non-technical reminders, very simple reminders, were especially effective, and they reached about 60% of the performance increase that we obtained with benchmark number 1, so with completely unbiased data. We found null results in changing the incentives of our programmers. So we could see this affected their effort, but not really their outcomes. And we actually found negative results when we gave technical advice to the programmers. That is, the technical advice in this experiment made algorithmic bias worse. If we then look at the programmer characteristics instead, we see they are broadly uncorrelated with bias in code. So that was true for demographic characteristics of the programmers. It was also true for the outcome of an implicit association test that our programmers went through. So this is a psychological test meant to elicit and measure implicit biases that people have. And we ran this test at the end of the experiment after subjects completed their machine learning task and completed the survey. However, the prediction errors were correlated within demographics. So this would imply that we might achieve bias reduction through averaging cross demographic. Now, moving on to the empirical details of the experiment, as said, we work with about 400 engineers. They were not told they are in a study. They were actually told they're developing a resume screening algorithm for a company. Our population was slightly more diverse than the software engineering population as a whole in the US. And we had two sources of subjects in the experiment. So about 20% were hired directly for a consulting project, and about 80% were recruited through an AI bootcamp for rising graduating CS majors. So 20% were hired directly, as said, with an ad similar to this. So we posted a job ad and we searched for machine learning programmers, while 80% of the sample was hired, they were in a machine learning bootcamp. And this was part of their assignment for the bootcamp. As training data, we use the PIAAC dataset coming from the OECD. This is administrative data, and it's a quite canonical dataset for cross-country comparisons of math literacy. So this is assembled by the OECD statistical group, and it's meant to be representative of the OECD countries. One drawback we have with the data is that we have inconsistent data about ethnicity. So we mainly focus on gender disparities here. And we uploaded on our website a cleaned copy of this data set. So one important element of the data set is that some subjects were assigned a random training sample from PIAAC. Some other subjects were assigned a sample featuring realistic sample selection bias. So they received a sample, they received math performance data only for people that were already doing math-related job. It's interesting that the PIAAC dataset allows us to know who in our data is already in math-related job. So in a way, this resembles the problem that companies often face when they need to create a hiring algorithm, but they only have data about people who had already been hired in the past. I'll now describe the other conditions more in detail. But we chose math in this data set because it's, of course, the topic of frequent gender stereotyping and also self-stereotyping that may lead to algorithmic bias. And also, it gave us objectively correct answers that we could use as ground truth. So the experimental design, as I said, this was an individual task. Programmers randomly were assigned to 1 in 4 conditions after a stratification. And the first group was the control group, the benchmark. This group only received biased training data without additional guidance. The second group received the same biased training data, so the data we discussed before with selected only among people that already are in math jobs, but they also received a non-technical reminder, which I will now go through. The third group received biased training data, the non-technical reminder, and also a piece of technical advice on sample selection corrections in machine learning that was based on the papers cited here. Then finally, the fourth group actually received representative training data. That was the first benchmark before. You might think there was some contamination across groups. In the paper, we go in detail about what we did to suppress this potential contamination across groups as much as possible. So this was the text of the non-technical reminder. So it was a very simple text, but it just reminded subjects that the expectations about who to hire may have been systematically wrong. And so the performance data that is available is only for workers like the ones that were hired in the past. So I won't go through it line by line, but you can see it refers to a biased social system, and it invites them to adjust their algorithm to account for discrimination in hiring. We also had a sub-treatment. So across all our 4 treatments, we assigned random performance benchmarks by MSc. These benchmarks were tied to the payoffs for the task. So consultants could get bonus money, and the bootcamp participants got bonus grades. So each programmer was randomly assigned to either an easy or a hard benchmark, and this created a random variation in the incentives they faced. Moving on to the results, we see that the great majority of our engineers used Python for this task. A small majority approached the task with random forests, but you can see a set of different machine learning tools. Some did linear models, some neural nets, many use an ensemble approach. When looking at gender variables, we see that 60% of our programmers directly utilize the gender variable in their algorithm. And by using this gender variable, programmers changed predicted math skills by 0.3 standard deviations on average. Then 40% of our programmers directly utilize gender proxy variables, so things such as household work. And by using these proxy variables, the programmers changed predicted math skills by 0.15 standard deviations. So our treatments did not significantly change this use of gender variables. The reminder group actually had a higher awareness. So when they answered the survey, they claimed to be more aware about this. But then the use of gender variables was also uncorrelated with programmer demographic characteristics and with their results in the implicit association test. Moving on to the main treatment results, so to compare these results, we need a way to measure bias. And of course, there's multiple ways to do so. Our metrics here are accuracy-based. So specifically, we measure systematic over or underestimation of ability given true performance, and also vice versa. So systematic over or under performance given estimation of ability by gender. So why do we focus on accuracy? Even if the decision maker has additional objectives, for example, if they have an explicit preference for diversity, having unbiased prediction still puts them on the efficient frontier. So our main results, I'm going to compare the various treatments with the biased data benchmark. So the group that received biased data and no additional indication or help. So ranking from best to worst, we observed, unsurprisingly, I would say, that the very best group was the group that received unbiased data, the better data. So they improved compared to the biased data group by 0.2 standard deviations. Interestingly, the second group was the group receiving the non-technical reminder. So they improved their prediction and their accuracy compared to the biased data group by 0.12 standard deviations. We found no effect for the different performance benchmarks, so for incentives, and we actually found a negative effect for the technical advice. So remember, the group with technical advice received the non-technical reminder and also additional technical advice. This made their performance worse. And if we try to understand what went on in that group from the survey, it seems that at least some people in that group got the technical advice, but were not fully able to implement it. And so wasted some time on that. While the people in the non-technical reminder group, they actually just tried to improve the algorithm as they knew best, and they managed to obtain, to reduce the bias more. When we analyze the programmer demographic characteristics instead, we see that our measures of algorithmic bias are uncorrelated with programmer demographic. However, the errors are correlated within demographic types. So this would imply that we could obtain a bias reduction by averaging across demographic types. So the men's errors are correlated with men's errors, but women's errors are uncorrelated with men's errors. So if we were to build a team, having men and women would allow us potentially to reduce bias. So in summary, in this broader fairness literature, we claim there is little empirical evidence that causally links programming practices to reductions in algorithmic bias. And we try to address this gap with a field experiment over 400 AI programmers. We found that simple, non-technical reminders are surprisingly effective. The technical advice instead was ineffective, and possibly this was because of implementation errors on the side of programmers. Clearly, nothing was as effective as having representative data. And when looking at programmers' demographics, we see that prediction errors are correlated within demographic groups, thus implying that potentially we could reduce bias by having groups coming from different demographic types.